Hey class. So we're ready to start in chapter 7. Notice that we're skipping over 7.1. That section's not in the course, but 7.2 and 7.3 are. 7.2 is the law of sines. So in this section, and actually in the next section, we're going to look at non-right triangles, right? So, our focus so far up in the class has been mainly on right triangles. So now we want to switch and focus on non-right triangles, or these are called oblique triangles, right? So an oblique triangle is a triangle that does not contain a right right angle. All right, so this is going to be our focus, like I said. So there are two types of oblique triangles. Right? So we can have an acute triangle, right? So an acute triangle is where we have all acute angles in the triangle, right? And then the other triangle that we can get is called an obtuse triangle. Right? So an obtuse triangle is where we have one obtuse angle, and then that leaves two acute angles. Right? And in case you forget, an obtuse angle is in between 90 degrees and 180 degrees exclusive, right? Meaning that we're not including 90 or 180, right? Because if an angle is measures 90 degrees, that's a right angle. If it measures 180 degrees, then that's a straight angle, right? So I think we talked about this like one of the very first sections, right? So then just a refresher on acute angles are between 0 degrees and 90 degrees exclusive. Right, so again, not including 0 or 90. An acute angle is in between, it's less than a right angle essentially. Obtuse angle is bigger than a right angle but smaller than a straight angle, right? So so what we want to focus on now is if we're given the length of a side, so if we're given the length of a side and any other two parts of an oblique triangle, we can solve that triangle. Right? So solving that triangle, what that's meaning is you're be able to find all the angles and all the side lengths of the triangle. Right? That's what we mean by solving. You're finding all the parts, all the measurements. Right? So when we have these, we actually have four distinct cases. right? So we have to know at least one side and then two other parts, right? Those could be two angles, those could be the two other sides, those could be an angle and a side, and so forth, right? So the four distinct cases, the first one is if you know two angles and any side are known, right? We refer to that as angle side angle or side angle angle, right? The second distinct case is two sides and an angle opposite of one of them are known, and that would be a side-side angle case. Right? So then the third is that three sides are known. Refer to that as side, side, side. And then the fourth scenario is when two sides and the angle between them are known. And that's referred to as side angle side. Right? So these first two cases, we're going to use the law of sines to be able to solve, right? That's what this section's on. The next section is on the law of cosines, and that's what we'll need the last four situations to solve, right? So the first two, we're going to use the law of sines, which is this section. And the last two scenarios, we'll use the law of cosines, which is the next section. Right. So now let me present what the law of sines is. So the law of sines states that if triangle ABC is a triangle with sides of lengths A, B, and C opposite of angles A, B, and C respectively, then the following is true. A divided by sine of angle A is equal to B divided by sine of angle B equals C divided by sine of angle C, right? Or we can just find the reciprocals of everything, right? The sine of angle A divided by A equals the sine of angle B divided by B equals the sine of angle C divided by C, right? So this is known as the law of sines, right? And if you have trouble this first statement here, right, what that's just describing is a triangle that looks like this, right, where maybe these are angles A, B, and C, where the side that's right across from angle A is little a, the one across from B is little b, and then the one across from C is little c. Right? It's just describing that picture. That's what that if statement is saying, right? That should be a capital C, right? So that's the law of sines, right? And I included on Canvas a number of extra practice videos for some of these problems from Patrick Just Math Tutorials, but I also included a proof of the law of sines if you're interested to see what that looks like, and that I believe that video is from Khan Academy. Right, so feel free to check those out on Canvas, right? So example 1, we're trying to solve triangle ABC, right? And just remember what that's meaning is we want to find all of the pieces, right? So we have A, B, and C, and then little a, little b, little c. I want to be able to find all of these pieces, right? That's what solve means. So angle B, remember capital letters are angles, and the lowercase letters are going to be side lengths, right? So we know capital B, angle B is 70 degrees. Angle C is 48 degrees. And then B is 15 centimeters, right? We want to be able to solve for all of these, right? So angle A will be easy to figure out, right? Because the sum of all the angles in a triangle is 180 degrees, right? So A is going to equal 180 degrees minus 48 degrees plus 70 degrees, right? Because basically I have a triangle. Here's A, B, and C. So I know this is 70 degrees. This is 48 degrees. Then this is just what I was saying, we would take the difference, right? Add those two up and then take 180 minus that sum, and that will give me angle A. Right, so 180 minus 48 plus 70 is 62 degrees, right? So that's 62 degrees. So I have that filled in. And then now to be able to find A and C, that's where I need to use the law of sines, right? So to figure out A, I could take sine of 62 degrees divided by little a equals, and then I'm going to want to use B here because I know the angle and the side measurement for B, right? So this would be sine of 70 degrees all divided by 15. You know, we could put centimeters, right? But I'll just know that each of these answers for A and C are going to be in centimeters, right? So then here's where I can just, this is like a proportion, right? I can just cross multiply. So A is going to be equal to 15 times sine of 62 degrees, all divided by sine of 70 degrees, right? So we can just cross multiply, right? So, just like in middle school when you did proportions, right? Same idea. So this would be the exact answer, right? So then we could plug this in to get an approximation. And see, we're supposed to round to 1 decimal spot, right? So this should come out to be 14.1 centimeters, right? So then to be able to find C, I recommend still using the information for B, because if you think about this, this answer for A, that's rounded, right? So if I can avoid using a rounded answer to get another answer, that's going to be better, right? So we can just say sine of 70 degrees divided by 15 equals sine of 48 degrees all divided by C, right? And just solve for C. So C would equal 15 times sine of 48 degrees all divided by sine of 70 degrees. All right, so that's my exact answer. Then the approximation for this is 11.9 centimeters. Right? So 11.9 centimeters. All right, so we've solved that triangle. So then I have another one, example 2. Right, so again, I'm going to want to find A, B, and C, the angle measurements, and I also want the side lengths A, B, and C. So angle A we know is 33 degrees, right? That's given. Angle B is 112 degrees. That's given. And then C is 16, right? And we don't know the units. This is just units, right? It's not provided. It's just in generic units length. So again, this is very similar to the first example. C is going to be equal to 180 minus the sum of 33 degrees plus 112 degrees. Right? Same rationale as before. That should come out to be 35 degrees. Right? So then, again, this, for C, what I just highlighted, these are exact answers. We didn't round 35 or 16, right? 16 was provided, and 35 degrees we were able to find exactly. So, to find A and B, it would be preferred to use the angle C and side C in both cases, right? So let me just get that set up. Right? So then maybe I want to find A first, where I would just fill this in. So sine of 33, sine of A divided by little a, right? And I can solve for that. So A would equal 16 times sine of 33 degrees, all divided by sine of 35 degrees, right? And then, so that's my exact answer, and this comes out to be approximately 15.2, right, rounding to 1 decimal spot, right? And when you're doing this, don't forget that your mode should be in degrees, right, because we're working in degrees here. So this is just 15.2 units, and then to find B, we would put sine of 112, right, sine of B here, and then little b. So then little b, so we just cross multiply and solve for B. So that would be equal to 16 sine of 112 degrees, all divided by sine of 35 degrees. So there's my exact answer. And then that decimal approximation comes out to be 25.9, right? If you plug that in your calculator, 25.9 units, right? Remember, we don't know if it's inches or feet or whatnot, so it's just generic units, right? So those are probably more of the basic examples to look at. Although I don't think law of sines is too crazy difficult if you know how to solve a proportion, okay? But objective 2, we get a little harder. It says solve a triangle, use the law of sines, side angle, the ambiguous case, right? So ambiguous means that something could have more than one meaning, right? So keeping that in mind, this will make sense, right? So the idea is we need to be careful with the side angle scenario because the given information could define a unique triangle, or it could define two different triangles, or actually no triangle, right? So let me explain each of these. So the law of sines ambiguous case, right? So the first one is we could have a situation where there's actually no triangle, right? So if I have a triangle that looks like this, right, we know what angle A is, angle B, angle C, and then this would be A, B, side C, and then there's going to be some height of the triangle given, right? So this is not a triangle because not all of the there's three sides, but all three sides are connected, right? We have an open part here. So in other words, this happens when A is less than your height of the triangle, right? So in other words, side A is too short to meet side C, right? So that's one example of that, right? Another thing that can happen is that we get one right triangle, right? So that just looks like, we have a right triangle. There's A, B, and C, so that's side A, side B, side C. So in this case, your A is actually your height of the triangle, right? So A equals your height, H. So we could say that side A is exactly equal to the altitude or the height of the triangle. Right. Another scenario that can happen is where we have one oblique triangle. Right. So an oblique triangle, we could just have like this example. So it's A, B, C. So this would be A, little b, little c, and then we would have some height of the triangle, right? So in other words, A is going to be greater than B, so you only get one triangle possible, right? So the oblique triangle and the right triangle, that's the option where we get one unique triangle, right? So there's two options for that, and then we've looked at the no triangle, and then notice the other thing that could happen is we have two different triangles. So let me show you that case. So we could have two triangles, right? So we could have one acute and one obtuse. Triangle be possible, right? So this is A, B, and C, and then draw this as B also as a possibility. So then that would be my height H. This is little a, little b, and then this side is little c, right? So you can see that there's two triangles possible, and maybe I'll draw the one possibility in a different color, right? So you can see that the one triangle is kind of the outside, right? Using this red little a as the side, versus the other triangle that, let me just outline that in blue, would look like this, right? So those are some possibilities, right? So in this case, H is going to be less than A, which is less than B, right? So in other words, side A intersects side C at an obtuse or acute angle, right? So either of those could be possible, right? That makes sense to have two different options because sine is, for example, positive in the first and second quadrant, right? So we might have a solution here. Maybe that's my reference angle, that's my reference angle. So I'm going to have one acute possibility and then one obtuse possibility, right? So it's possible that I could end up with possibly two triangles, right, when I'm solving for sine. And we'll see an example of that, right? So this first one, first example, we want to be able to solve triangle ABC with given angle A and then two sides, right? So angle A, I'll just fill these in. Angle A is 49 degrees. Angle B and C we don't know. Little a is 32. Little b is 28. And little c we don't know, right? And these are just in generic units, but I just won't write that this time, but you could if you wanted. Right? So, probably the easiest place to start would be to find the measurement of angle B using the law of sines, right? So we could say, the sine of 49 degrees, so the sine of A divided by little a equals the sine of big B divided by the sine of little, not sine, but just divided by little b, which is 28. Right? So I'm just trying to solve for b. So I'm going to get sine of b by itself. So sine of b would be equal to 28 times sine of 49 degrees, all divided by 32. Right? And in this case, if I pull out my calculator, right? So let me make sure my mode, I want to be in degrees for this. So if I just put in what we had, 28 times the sine of 49 divided by 32, right? So that's a positive solution, right? Positive number. It's in between -1 and 1 like we would expect, right? We would hope that that's happening. So since this is positive, right? In other words, this is roughly 0.6, I believe, right? 0.66, which is positive. So sine, all students take calculus, is positive in the first and the second quadrant, right? So if I do arc sine of that answer, I get the reference angle, which is roughly 41.3, right? So this, this is x prime and this is x prime, the reference angle. So I found x prime to be equal to the sine, then arc sine of 28 times sine of 49 degrees, all divided by 32, right? Which is approximately, 41.3 degrees, right? So that's 41.3 degrees. To find this guy, right, this other, to find this angle here, we would take 180 degrees minus 41.3 degrees, right? So 180 minus 41.3 gives me 138.7. Right? So those are the two possibilities. But notice if I take 138.7 and add it to the angle I already know, 49 degrees, that's going to bump me over 180 degrees, right? So this one doesn't make sense. This one can't be possible because we're stuck in a triangle, right? So we need to throw that one out. So in this case, the only possibility for angle B is 41.3 degrees, right? So then I can find angle C now, right, by taking 180 degrees minus the sum of the other two measurements, So that gets me 89.7 degrees. So that's 89.7 degrees. And then now I can find C by using law of sines again, right? So I would have sine, I'll just do A, sine of 49 degrees. Oops, and that's not a 0, it's a degree symbol, right? Divided by 32 equals sine of 89.7 degrees all over little c, right? So little c is going to be equal to 32 times sine of 89.7 degrees, all divided by sine of 49 degrees, right? So if we enter that in, 32 times the sine of 89.7 divided by sine of 49, we get 42.4, right? So that's approximately 42.4. Right? So I found, I solved the right triangle then, right? Or it's not a right triangle, I solved the triangle. I found all of the angle measurements and all of the side lengths. Right? So we have another one to try. Right? So we just start off, I like to just start off by making, listing all my angles and sides. So B is 31 degrees, little b is 3, little a is 6.2, and that's all we know, right? So I could start out by finding angle A, right? So using the law of sines, that would be sine of A divided by, that's 6.2, equals sine of B, which is 31 degrees, divided by 3. So sine of A is equal to 6.2 times sine of 31 degrees divided by 3, right? So that's the exact answer. So if I put this in my calculator, 6.2 times the sine of 31 degrees divided by 3, we get roughly 1.06. Right? But wait a minute, we should know that sine of A should be in between -1 and 1, right? Well, this answer is bigger than 1, so it doesn't fit, in the range of sine, right? That doesn't make sense. So when that happens, we know that this is going to be a no triangle case, right? That's the case where, we have this, this kind of situation going on, right? Where we have this gap going on, right? And this is actually going to be angle A, right? Since angle A doesn't come out to a value, that's going to be the one that doesn't actually have an angle going on here, right? Right? So that's what that looks like and how to recognize that. Example 5, we're actually going to find that this is a scenario where we could have two possible triangles, right? So we've had an example of each of the cases, if you will, right? Where you have one unique triangle, one that's not a triangle, then the other is where we have two triangles possible, right? So let me just fill this in. Right? So what we know is this is 40 degrees. I know that little a is 22, little b is 25, and that's all we know, right? So maybe a nice place to start would be to find angle B, right? So sine of angle b divided by little b, which is 25, would be equal to sine of a, which is 40 degrees, divided by little a, which is 22, right? So sine of b is going to equal 25 times sine of 40 degrees divided by 22, right? And if you put this in your calculator, right? So take 25 times the sine of 40 divided by 22. That comes out to be approximately 0.730, right? So we get a positive value, right? So if I want to find b, right, then we would do sine inverse of 25 times sine of 40 degrees all over 22, right? And if you type that in your calculator, you should get that comes out to be approximately 46.9 degrees, right? But something that we have to consider is sine of b was positive, and sine is positive, just like we talked about before, in the first and second quadrant, right? So this angle is 46.9 degrees, and this reference angle is 46.9 degrees. So in order to find this angle in the second quadrant, I'd want to take 180 degrees minus 46.9 degrees, which gets me to 133.1 degrees, right? So these are the two possibilities for angle B, right? And notice if I take this angle and add 40 to it, we're going to be less than 180. Same thing with this angle, right? If I take 46.9 and add 40, I'm going to be, less than 180. So both of these are, possibilities for angle B, right? We have two possibilities. So we could label this as triangle 1, and then we can have a triangle 2, right? So let me just fill in what we know so far, right? So this would be 22, 25, 40 degrees, right? Because those were all givens. And then one possibility is that this is 46.9 degrees, and this could be 133.1 degrees, right? So let me maybe stick with this blue for triangle 1, and I'll stick with red for triangle 2, right, from here on out. So let me draw a black line just to kind of separate that work, right? So let me use the blue to work with triangle 1 first, right, because I don't want to get my letters confused. So if I want to find angle C, that would be equal to 180 degrees minus the sum of 40 degrees plus 46.9 degrees, which that's going to equal, so if I take 180 minus 40 plus 46.9, we get 93.1 degrees. Right? So then now I could use the law of sines to figure out C. So sine of 93.1 degrees divided by little c is equal to sine, I'll use A, so 40 degrees divided by little a, which is 22. So this gives me that C equals 22 times sine of 40 degrees divided by sine of 93.1. That's a degree symbol. 93.1 degrees. Right? So this comes out to be approximately, let's see, 22. Whoops, excuse me. I wrote these in the wrong spot, right? Because when we cross multiply, I'm multiplying these two things together, right? So it'd be 22 times sine of 93.1, and then divide by the thing that's across from what you know, or what we're looking for, so that this should be 40 degrees, right? So if I plug that in, 22 sine 93.1 divided by sine of 40, that comes out to be approximately 34.2. right? So I have the first triangle completely solved. I still need to figure out triangle 2, right? So let me just do that work right here. So C, right, is going to be equal to 180 degrees, angle C, minus the sum of the other two angles. So 180 minus the sum of 40 and 131.1 degrees, that comes out to be 6.9 degrees, right? And then I need to do the law of sines to figure out little c. So sine of 6.9 degrees divided by little c equals sine of 40 degrees, all divided by 22, right? So little c is going to be equal to 22 times sine of 6.9 degrees, all divided by sine of 40 degrees, which that is approximately equal to 4.1. Right? So there's all of those parts, right? So we had two triangle possibilities. Right? All right, so now we're ready for objective 3. So objective 3, we want to compute the area of a given, of a triangle given side angle side, right? So in this situation, the way to think about it is I have a triangle. Let me just label A, B, and C. So this would be A, this would be little b, and this would be little c. And then, of course, this triangle is going to have some height to it. Right, and let me actually draw that as a dashed line, right? Because that's just like a measurement. Something that we can, gather from this is what happens if I calculate the sine of angle A, right? So the sine of A, right? So I'm thinking about this as being a right triangle. So sine of A is going to be equal to the opposite, right, which would be h, divided by the hypotenuse, which would be little b in this case, right? So this gives me that h is equal to b times sine of A, right? So that's just by multiplying both sides by b. So, the reason why I did that is, so now I have, an expression for the height of the triangle, because the area of a triangle is equal to the height times the base, right? And the base of a triangle is always going to be the side that's perpendicular to the height, right? So in this case, this part is the base, right? Because things that are perpendicular, they meet at a 90-degree angle, right? So this would be equal to the height, which would be b times sine of A, and then times the base, which is this little c, right? So in other words, in the area of a triangle is 1/2 base times height, right? So this would, I forgot a factor of a half out front here. So this would be 1/2, right? So then what this turns out to be, just rearranging some things, this would just be 1/2 b times c times sine of A, right? And that just makes it a little nicer to write if we write the trig function last, so that way it's clear, what you're actually taking the trig function of, right? So area of a triangle is 1/2 base times height, right? All right, so let me just make a statement here. So area of a triangle given two sides and the angle between them, right? Let's call that the title. So for a triangle, triangle ABC with side lengths A, B, and C across from angles A, B, and C, respectively, the area of the triangle is given by area equals 1/2 BC times sine of A, or area equals 1/2 A times B times sine of C, or the area equals 1/2 AC sine of B, right? So in other words, if you notice, to find the area of the triangle, you're just going to take 1/2 times the product of two sides, and then times sine of the angle that's between them, right? And that's going to be the other letter, right? The missing letter, if you will. You know, something that's important here is I can actually get the other equations just by changing what's the base, right? So if I erase some of this in the previous picture, right? So maybe I want like side B to be the height, right? Then what I would want to do is measure the height. When you measure height, you stand straight up, right? Perpendicular, right? So this is my base, and this would be my height. Then you would do like the same kind of work, right? To come up with another equation. And then to get the other one, right, you would, if you wanted A to be the height, then you would come in and this would now be my height, right, and so forth, right? So you can get the other just by changing what your base is and drawing your height appropriately. You can get the other equations just like the work we did before, right? So example 6 is an example of this. So a triangle has sides of 12 meters and 6 meters, and the angle between them is 76 degrees. Find the area of the triangle, right? So the area of the triangle is just going to be 1/2 times the product of the side lengths, right, times the sine of the angle between them, which is 76 degrees. So I can simplify this part, right? That would, 1/2 times 12 is 6, so that'd be 6 times 6, so we get 36, and then meter times meter, we get meters squared, right? And I'll actually put that at the end. I'll just do 36 sine of 76 degrees, and the units is meters squared, right? So we took meter times meter. So that would be the exact answer, right? And then we want to round to 1 decimal spot, so if I put this in my calculator, you should get 34.9 meters squared, right? Because we're told to round just to 1 decimal spot, right? All right, so the very last, we're ready for the very last page. There's 2 examples left. The last objective is being able to have some applications of the law of sines, right? So first thing we want to do is just be able to draw these scenarios. So example 7, it says to measure the maximum height of a water fountain in a to measure the maximum height of the water in a fountain, a trigonometry student measures the angle of elevation of the maximum point to be 25 degrees. At a point 30 feet farther away along the same line of sight, the angle of elevation is 18 degrees. If the eye level of the student is 5.5 feet, find the maximum height of the water, right? So let me try to draw this the best I can, right? So we have a fountain, and then the fountain, the water, is coming out, and there's going to be some maximum height, right? Maybe this point is the maximum height. And then there's a student standing on the ground, right? And he or she, it doesn't say, right, is 5.5 feet tall, right? So the angle of elevation, right, what that's going to look like is they're looking up at the tallest point where the water's going. And then if I draw a dash line here that's horizontal with the ground, right? So like this is the ground, right? Then this part, this angle, is the angle of elevation, which would be 25 degrees, right? And then what's said is the student, steps back 30 feet. Right? So he's still, 5.5 feet tall. And then we got a new angle of elevation. So actually, let me use a roller here. Probably make this a little easier if I use a roller. Right, so that's probably pretty good. Right, and then if we bring this over, we just have a new angle of elevation, which is, let me go to the roller, 18 degrees. That's 18 degrees, right? So basically, if once I have that, I can kind of pull this apart into this picture, right? So if I just draw these, try to draw this picture into the triangles that we have, we'll have something like this. Whoops. Right, where this is a right angle. So this is the I'll just call that H. That's basically the height of the water that's above the person's head. Right, so we'll let that be H. And then we know that this is 25 degrees, and this is 18 degrees. We know from here to here is 30 feet. I think that's all we know so far, right? So I can fill in some more parts. So I can find this angle pretty easy, right? Because notice 25 degrees and that angle, these are going to be supplementary angles, right? They make a straight angle. So if I take 180 minus 25, that will give me that part I marked in black, right? So that would be 155 degrees. And then I could find this angle pretty easy, just by taking, 180 minus the sum of 18 degrees and 155 degrees, right? And that comes out to be 7 degrees. And then I could find this angle pretty easy because that's a 90-degree angle. So I would just, then these two angles, this one and this one, would have to be complementary angles, right? Have to add to 90, so that would be 65 degrees. And then I could maybe label this as X, right? So to be able to figure this out, I'm trying to find H, right? So in order to find H, I need to know one of the sides, right, of this triangle here. So the easiest thing to do would be to try to find this side here, and we'll call that, let's say, y. Right? So to be able to find y, I need to use the law of sines, right, with this triangle, this other, the obtuse triangle, not the right triangle. So we could figure that out by doing sine of 18 degrees divided by y equals, and then I know this side, so I want to use this with that angle, so that would be sine of 7 degrees over 30 feet. Right? So y would be equal to 30 times sine of 18 degrees divided by sine of 7 degrees. Right? So this will come out to be approximately 76.1 feet. Right? So that's what y is, 76.1 feet. So then to find h, I'm just going to apply the law of sines again, right? So I would have sine of 90 degrees, right, this right angle, divided by 76.1 feet equals, and then I want to find what h is, so I can put h here, and its angle across from that is 25 degrees. So then h would equal 76.1 feet times sine of 25 degrees, all divided by sine of 90 degrees, right? Well, and sine of 90 degrees is 1, right? So I don't really have to worry about that. But this should come out to be I don't have to worry about the denominator, right? So this comes out to be 32.148. Right? So then that's not the actual answer though, right? Because remember, this h part is this measurement, this height, right? You know, just that part. So what I need to do is add in the height of the student, which is 5.5 feet, right? So the maximum height of the water would be equal to 5.5 feet plus h, right? Which comes out to be approximately 37.6 feet. Right, so we're asked to round to the nearest tenth of a foot, right? So there's the final answer, right? So this was, pretty involved, right, as you would expect with an application problem, right? So then I have one more here to try, and in this one, we have an 80-foot flagpole is located at the top of a hill. An observer 220 feet down the hill measures the angle formed by the bottom of the pole to the top of the pole to be 17.7 degrees, right? So in this problem, I took this out of the book, and it provides a picture for you. So rather than giving that picture in the notes, I thought I would just draw it here, right? So let me try to draw this picture for you. Right, so this is the hill, right, and then this is the flagpole. So that flagpole, that's 80 feet, and then the angle from the top of the pole to the bottom pole is 17.7 degrees, so that's this part, 17.7 degrees. And then what we're trying to find is the angle of inclination of the hill, which is actually this part, right? So we can maybe call this x, right? So really the what we're trying to find is we want to know what x is, right? So the way to think about this problem is if I extend this line out and then draw in a line that's parallel with the ground, right? So like this is the ground, if you will, right? Like ground level. Then this angle here, maybe we'll call beta. That's actually the same. This is equal to x, right? So the measurement of angle beta will actually be equal to the measurement of angle x, right? So that's because we have a line intersecting two parallel lines, right? So that's just from from geometry days, right? So those are what we call corresponding angles, right? So like if you extend this out, right, then the situation we have is we have two lines and then one line intersecting those, right? So this angle is going to be equal to this angle, right? Or in other words, this angle will also be equal to this angle, right? So to be able to figure that out, what I would really like to know is what z is, right? And something to note, though, since we're looking uphill, that this angle, maybe we'll call this y, and this angle z, right? So I think I mentioned z, and I forgot to draw that in, right? So if I label that y and that z, if I want to find z, it's important to note that y is going to have to be greater than 90 degrees since you're looking uphill, right? So it wouldn't make sense for that to be an acute angle since you're looking up the hill, right? So what that means is that z is an acute angle, right? It would be forced to be an acute angle. So that's important to know because actually when we solve for z, we could get two possibilities, right? We could get an acute or an obtuse option that would work here. So that's why that observation is important. All right, so let me get rid of that. So then using law of sines, right, we could use, say, sine of 17.17 degrees, divided by 80, right, because that's the side, the flagpole height is the opposite side for the 17.17 degrees. And then that's equal to sine of z divided by, I forgot to label this part. That's important, right? We're 220 feet down from on the hill, right? So that'd be 220 feet here, and this is 80 feet. So then sine of z would be equal to 220 times the sine of 17.7 degrees divided by 80 feet, right? And this is feet. So this comes out to be approximately 56.7 degrees, right? So again, in general, we're going to have two options for sine. So this would be 56.7 degrees, right? And this guy would be 180 minus 56.7, right, which is 123.3 degrees. But we're actually going to throw this option out because of this fact, right? That this part has to be obtuse, so that forces z to be acute angle, so it's going to be stuck in the first quadrant, right? So we know that for z. Whoops, I shouldn't have labeled that way. So z would be equal to inverse sine of 220. I won't write the feet. 220 times sine of 17.7 degrees divided by 80. Right, and that's what was approximately equal to 56.7 degrees, right? Z, not the sine of z. Sine of z would have to be in between -1 and 1, right? So just make sure you fix that notation. Sorry about that. So then, now that I know z, I can figure out what y is, right? So y is going to be equal to 180 minus the sum of 17.7 degrees plus 56.7 degrees. So if you do that in your calculator, that comes out to be 105.6 degrees. Right? So then, this is getting a little messy. Let me maybe change colors here. I'll change to green. So, this part makes a straight angle, right? So maybe I'll call, let me get rid of the 80 feet. I'll call this this angle alpha, right? Use beta. So alpha is going to equal 180 degrees minus y, right? Because y and alpha have to add to be 180 degrees. They make a straight angle. So this would be 180 degrees minus 105.6 degrees, which comes out to be 74.4 degrees, right? And I wanted to know that because, let me see if I can pick another color here. Maybe do like, I don't know, we'll just do like this light purple here. So then between here and here, that's going to be 90 degrees, a right angle, right? This is a right angle between the flagpole and the ground, right? We're imagining the flagpole standing straight up. So then if I want to find beta, that's going to be equal to 90 minus alpha, right? Which would be 90 degrees minus 74.4 degrees, which is equal to 15.6 degrees, right? So remember that measurement of angle beta is equal to the measurement of angle x, which is what we were after. So they're both equal to 15.6 degrees. So that's the angle that we were after. So that's the solution, right? 15.6 degrees, right? All right, so that's all I have for this section. So don't forget, I posted some additional videos you can check out. So please do that, especially if you're having some trouble with this section, right? And if you're having trouble, also, feel free to let me know, and I'll be glad to help. All right, thanks.